Hello YouTube. This is an introduction to metric spaces. So what exactly is a metric space? So if we'll have a set which we'll call X, and we have a function defined on it, which we refer to as D, because it's usually referred to as the distance function. This distance function must hold true for certain fundamental properties. Then one can define the set X in conjunction with its function, a metric space. So, the fundamental principles that must hold true for this distance function is, the first one is D must be real valued, finite and non-negative. Non-negative just means it's not supposed to be a negative number, so it can be 0 or greater than 0. The distance function equals 0 if and only if the two elements are equal, so when x and y equal. Symmetry must hold, meaning the distance function from x to y must equal the distance function from y to x. And then fundamental property 4 is what's referred to as the triangle inequality, and that's where the distance between 2 points is always shorter than or equal to the distance between the point and a third point, and the third point and the eventual y value. Schematically, you can show that with a triangle. The best way to visualize it is in a two-dimensional space where I'll have an x and a y, and if I take the distance from x to z, which is a third point, and the distance from z to y, then I'll end up with a longer distance than the direct or shortest path between 2 points. A very nice example of this would be if I had in a two-dimensional space, if I had a value x here and a value y there, and my value z here, the distance between these 2 points will always be shorter than the distance here plus to that point there, which makes sense. In two-dimensional, it's very simple to visualize. It might not always be so simple to visualize in a much more general sense, but this triangle equality must always hold true. So let's look at a very simple example to explain or wrap the fundamental properties in a more practical sense. So let's look at the following example. It says, show that the set of real numbers R and the function D defined by the absolute value of the distance between x and y, or rather, instead of the distance, the difference between x and y. So we must take the absolute value of that, and we should show that this defines a metric space. So let's see. M1. So M1 says, if you remember correctly, that the distance function must be real valued, it must be finite, and it must be non-negative. So since we know that x and y are elements of R, if I take the difference between x and y, those will again be an element of R. And if I take the absolute value, the difference between two real values, I'll again end up with a positive, or at least 0. So it's going to be a non-negative value. That's something very simple you can state. You don't need to prove that, because we know that the difference between two real numbers, if you take the absolute value of that, it will be positive. That's the definition of an absolute value. And since x and y is an element of R, x minus y will be finite, because we take the difference between two finite real values. So that's a very simple one to prove, nothing difficult there. If we go to M2, M2 says that the distance function is 0 if the two values, the two elements are are equal to each other. So, and this is an if and only if statement. So we have to prove it both ways. So if we say the distance function between x and y is 0, that implies that the absolute value of the difference between x and y is equals to 0. But that means that x minus y must be equal to 0. And if I add y on both sides, I get to the result, which is that x equals y. Very simple. The converse says that if x equals y, and if I subtract y on both sides, I get x minus y equals 0. Taking the absolute of both sides, I get the absolute difference is equals to 0. So M2 holds. Again, very simple one to prove. Not difficult. Well, the R space is very easy to prove, but it's merely to explain the concept. So M3 says this is symmetry. So this says where the distance from x to y must be equal to the difference from y to x. So the difference or the distance function of x and y equals the absolute difference between x and y. So if I then take out as a common factor minus 1, I end up with minus 1 bracket y minus x. We know that the absolute value of minus 1 is 1. That's again the definition of an absolute value. So then I'll end up with y minus x absolute equals then the distance from y to x. So M3 holds. Now for the last one, M4, this is the triangle inequality. So that says that the distance, as you know, between x and y must be less than the distance between its triangular movements, or distance between the one element and a third one. And yeah, you get the idea. So yeah, I did a simple addition and subtraction where we just basically added with 0. So we started off with the absolute difference between x and y. I then add 0 in a simple way by subtracting z and also adding z. And then we know that the absolute, if I take the absolute of the one plus the absolute of the other, this result will be greater than this result. Now, this might not be very directly clear from the start. For those that it is, then great for you. But with a simple example, if you take the R line, you'll have the point x here and y there. And then I can plot 3 different scenarios. One where z lies on the left side of x, one where z lies between them, and one where z lies to the right of y. And in all 3 cases, if I take the absolute distance between these 2 points and the absolute distance between z1 and y, then the addition of those 2 will obviously be greater than the absolute distance between x and y. If I take a value between them and I add the absolute distance between these 2 and the absolute distance between these 2, it will actually be equal to the absolute distance between x and y. And there holds the equal part. If I take the other point here, if I add this absolute distance and I add this absolute distance from x to z2, then that will obviously be greater than the absolute distance for x and y, which is just a simple visual representation of why this holds true. And that is the simple gist of a metric space. Now, I've obviously used the R space to show this, but you can make the space actually very general, and this must hold true. And in future videos, we'll explore some more difficult problems. We can also look at metric spaces, or rather spaces with distance functions that is not a metric space, so that does not hold true. So in the next videos, I'll handle that, and I'll show you some more difficult examples of how to actually prove that something is in fact a metric space. For now, Have a wonderful day. See you. Bye bye.